announcement to those from the media. Please see me before you leave back for the sessions.
Don't do that. Okay.
Something to do with lunch.
It's very energetic. No badge. No badge.
Okay. Good afternoon. Welcome to day 2 of the press briefings at the 47th DPS meeting here at National Harbor. My name is Dr. Vishnu Reddy. I am the press officer for the DPS. Today we have a very exciting panel. To my far right is Dr. Apostolos Christou from Armagh Observatory, and he's going to talk about Mercury. Next we have Dr. Terry Hurford from NASA Goddard, who's going to talk about Phobos. Next we have Dr. Robin Canup from Southwest Research Institute, and she's going to talk about lunar volatiles. And finally we have Dr. Jean-Luc Margot from UCLA, and he's going to help us define what a planet is. They're going to come and do presentations, and I will be back to moderate the questions. That I'll ask Phobos.
Okay, so good morning. My name is Apostolos Christou, and I'm going to talk to you about this strange beast called the exosphere of Mercury. Right, so okay, we call it surface-bounded exosphere. So what is it? This is a cloud of atoms that surrounds every airless body in the solar system. It is extremely rarefied. It's in fact thinner than any vacuum you can conceivably make in the laboratory. But by studying it, we have learned that these entities are very dynamic. They have weather, they have seasons, so they are very exciting objects to study. So when we get the chance to look at one up close, we grab it with both hands, because then we can apply what we learn to other objects like the moon, Mercury, and the asteroids. Okay, so our short story begins with the messenger mission to Mercury. It spent 4 years observing, among other things, the exosphere of Mercury. In particular, it measured the amount of the metal calcium in the exosphere. So this is the same stuff that your bones would be made of. What it found is that the calcium varies as Mercury moves around in its orbit, and this pattern would repeat every Mercury year. In particular, there is a peak in the calcium emission, which I show it in the plot at around 25 degrees after Mercury passes through the perihelion in its orbit. Now, there's a paper that came out by Rosemary Killen and Joe Hahn at the beginning of this year, where they tried to explain this variation as a result of calcium thrown up from the surface by impacts with dust orbiting the sun. Now, the model works pretty well, but they had a difficulty fitting the peak at 25 degrees. So what they proposed, that the peak is caused by the dust stream along the orbit of Comet Encke. Now, so this dust stream would be the same structure that would cause meteor showers in the Earth's atmosphere. So this is quite interesting. So I decided to have a look. Okay, so yes, so okay, so there is a fly in the ointment here, and the fly is that the calcium peak is observed at 25 degrees, but if you look at where the comet intercepts the orbit of Mercury, the stream should hit Mercury much later on, about 40 degrees later on. So this needs some explaining. Okay, so what I did is I created a model to simulate how the stream formed. I found that a key ingredient in the solution to this problem is a force called a pointing Robertson drag. So this is caused when the dust absorbs sunlight and re-emits it as heat, and it acts like a tiny thruster that's continuously on, like an ion engine, if you like. So over a long period of time, like thousands of years, the orbit of the grain will be changed significantly. Okay, so this is the result. So here I show two simulations of the stream. The white points represent grains that were simulated for 10,000 years, and in a model where I only allow the gravity of the planets to affect the orbits of the particles. Okay, so what you see is that the particles simply spread along the orbit of the comet, and they hit Mercury well away from the calcium peak. The red grains are basically the same simulation, but now I have turned pointing Robertson drag on, and as you can see, the intersection point between the stream and Mercury's orbit are pretty much agree. So you can see that this very small force has a really important effect in understanding where the stream of Encke is in space. So if there's one lesson learned from this little piece of work, is that, right, we already knew that impacts are important in producing these surface bounded exospheres, but now we can tell with reasonable confidence that cometary streams can also have a very significant effect, and also an effect that repeats over different planetary years. So I'll stop here, and I will hand it off to Terry Hurford.
Thank you. I'm going to talk a little bit about Phobos and how its surface might evolve from its decay of its orbit. I've got a few slides to kind of introduce the concept of what's going on Phobos, and then the results of the work. Phobos is a unique satellite in the solar system in that its orbit is shrinking and it's falling into its parent planet. It orbits Mars, and this graphic here on the left kind of shows you what's going on. Anyways, that's not what I want to do. All right. The graphic kind of shows what's happening with the orbit. Mars is pictured in the center, and the mass of Phobos wants to raise a tide on Mars, and that tide wants to be aligned perfectly with Phobos. But because Phobos is orbiting faster than Mars rotates, it moves ahead of that tidal bulge. And so that tidal bulge on Mars stays behind Phobos, and it saps energy from Phobos's orbit over time. And that causes the orbit to then decay in toward Mars. Phobos is very unique in its geology. Here on the picture on the right, you can see all these series of grooves on its surface. And so we think that that might be kind of signs of that this body is starting to break apart tidally, and these are kind of the first evidence of the tidal deformations of Phobos. Eventually, Phobos will be ripped apart before it hits Mars' surface. So here's a quick movie kind of also to kind of show what's going on. So as Phobos gets closer and closer, it gets more and more tidally distorted because of the gravity of Mars. And so in this movie, we just have a Phobos that starts off as spherical, and as the orbit decays, it becomes more and more oblong shaped. The shape of Phobos causes, the deformation of Phobos causes stresses on the surface, and we're going to look at those stresses and see if we can link them up to the grooves that we actually observe on the surface. As it gets pulled into more of an oblate shape, the stresses right at the sub-Martian point and anti-Martian point are tensile, and in the regions kind of in between, you get a mixture of both tension and compression. And so this slide kind of shows the meat of the results, so I'll take a little bit of time to describe it now that you've got the background on what's going on in Phobos. The plot on the right shows a lot of things going on. So first, you can see the stress field, which is in the black and white. And so this plot represents the surface of Phobos. We have longitude and latitude, and at any of those tick marks, you can look and see what are the stresses on the surface. If you see a black bar, it's tension, and if you see a gray bar, it's compression. And again, in the sub-Martian point and the anti-Martian point, you have only tension in both directions. That's the point where the planet is being kind of pulled toward Mars. And then in the interstitial regions, you can see a mixture of both tension and compression. We've also, on this plot, mapped the location of a lot of the prominent grooves on Phobos. And we've colored them to we've done an analysis to how well they align with this tidal stress that we produce because of the infall of Phobos toward Mars. And so the fractures that are painted red are perfectly aligned with the tidal stress field. And by perfectly aligned, we mean that these things probably formed in tension and their orientation is perpendicular to the local tension. So the tension is pulling the surface apart, and you form a fracture perpendicular to that pull. The fractures in purple aren't well aligned with the tidal stress field, so they might be formed from a different mechanism. And in the session this morning, a likely mechanism is that when we have cratering events on Phobos, it throws up debris, and that debris reaccretes on the surface and forms those grooves. And then we got some grooves in gray. They're consistent with tidal stresses, but their orientation isn't diagnostic of tidal stresses, so we just haven't analyzed those. But the stress field that we get from just the recent orbital migration of Phobos can produce hundreds of kilopascals of stress on the surface, and we think that's sufficient to break the surface and form the grooves. And so that's our conclusions, that the orbital evolution is driving surface stresses, and those surface stresses are driving the geology that we see on Phobos. This is really exciting because this means that the group formation might be ongoing and actively occurring now. So, Phobos has been migrating inward for pretty much the age of the solar system, but the grooves can still be formed today. Many of them are old, some are younger, and it's still occurring now, so it's something that we should be able to observe going on now. And also, Phobos is a great analog for exoplanets. We can't image the surfaces of these planets directly, and many of these planets spiral into their parent host stars, and they're tidally locked. So if we think about rocky planets around other stars that are migrating inward toward its host star, they're going to be pulled apart too, and the stress states on the surfaces are likely to be very similar to what we observe on Phobos. And so that's the story, and with that I'll give it to Dr. Robin Canup from SWERI to talk about the moon.
So we're looking at the formation of our moon, in particular whether we can explain one of the primary compositional characteristics of the moon within the context of the so-called giant impact theory. So in many ways, the lunar samples are chemically indistinguishable from Earth rocks, but perhaps the most notable difference is that the moon rocks are relatively depleted in volatile elements. So volatile element is just an element that vaporizes readily as a material is heated. And when we look at the moon composition compared to the Earth composition shown on this plot, we see that it's depleted in the so-called moderately volatile elements, including sodium and potassium by a factor of a few, and even more strongly depleted in the more volatile elements, including notably zinc. And water, which is a very common volatile element that we think of, is still more volatile too. So what caused this relative depletion in volatiles in the moon has been unknown. We think the moon formed as a result of a giant impact with the Earth. Such an event would certainly heat up and partially vaporize the protolunar disk of material it places into orbit around the Earth. And so there's been this idea for decades that the vaporized volatiles escaped, and that's why the moon is lacking in them. But actually, if you look at the conditions in the disk, this seems very unlikely, primarily because the escape velocity from the Earth in the region where the moon forms is many times the expected thermal velocity for these vaporized species. So we're exploring an alternative, namely that we probably had a closed system without escape, and that the moon is depleted in volatile elements because it preferentially accreted volatile pore hot melt, while its essentially component of volatiles was preferentially accreted by the Earth during the moon's accumulation after the giant impact. So we imagine a situation after the impact where we have this hot disk of material around the Earth. In the inner region of the disk, in the dynamical region akin to where we see Saturn's rings, the disk would have been dispersed and a mixed vapor-fluid state. It would tend to spread radially with time. Outside this region is where condensed clumps of material can collide and coalesce to form a growing moon. And so what we've done is we've combined a dynamical model for the moon's assembly from such a situation with thermal and chemical models to predict the volatile content of the material delivered to the moon. So this is an animation of the dynamical simulation of the moon's assembly. So we're looking at the system on edge. The vertical dashed line is the Roche limit. So exterior to that, the material is shown in black. That's where the accretion of the moon will occur. And the inner disk is shown in orange, and its mass is decreasing with time as a function of its spreading onto the planet and out beyond the Roche limit. First thing that happens is an object containing about 40% of the moon's mass accumulates rapidly from material in the outer disk. Then starting about 17 years, this inner disk spread beyond the Roche limit and began feeding additional material to the moon, and that's shown by the orange growing layer on the moon. But that accretion process doesn't persist indefinitely. The moon its orbit expands away from the disk, and when that happens, we transition from a regime where the inner disk material is accumulated by the moon into one in which the moon is scattering material from the inner disk back into the disk and onto the Earth. And so at that point, the moon's accretion ends, and from that point forward, the remaining inner material is accreted by the Earth instead of by the moon. So we combine that model with a treatment for the temperature of that material that's coalescing at the Roche limit. And our predicted temperature is shown in the middle plot by the black curves, as well as a chemical model for the melt at the conditions at that point. And you'll see the resulting condensation temperatures we predict for the depleted species, some of them, potassium, sodium, and zinc. Now the plot on the right shows the fraction of the moon accreted as a function of time. And so you can see there's this rapid cutoff at around 100 years where essentially the moon's accretion stops. The take-home message is that we find as the moon accretes this last about half of its mass from the inner disk, the inner disk material is too hot to contain substantial volatiles. And that eventually the inner disk cools, shown by the declining black dashed line in the middle curve, and the volatiles will condense. But by this point, the moon has evolved far enough away from the inner disk that it's no longer efficiently accreting that material, and that volatile rich material ends up preferentially back on the Earth. So it looks like even if there's no escape from the disk, which seems likely, the final tens of percent to half of the moon's mass is going to be depleted in volatiles just as a result of its accretionary dynamics. And the overall model suggests that a heterogeneous distribution of volatiles in the moon's interior. The initial, say, half of the moon that accretes rapidly from the outer disk material may have retained its volatiles, and those would be preferentially found at depth. Overlying that would be an equivalent layer hundreds of kilometers in depth of this very volatile pore material from the inner disk. Thanks. Turn over to Jean-Luc.
All right. I would like to describe a quantitative criterion for defining planets. Now you all remember the 2006 IAU resolution in which a celestial body is considered to be a planet if A, it orbits the sun, B, it is nearly round, and C, it has cleared its orbit. Now since 2006, we've discovered thousands of exoplanets, and none of these bodies can be classified with the current official definition of planets. So we have a problem. We have thousands of objects without a classification. So the purpose of this work is to come up with a classification that can apply to both the solar system and exoplanets, and there's several desirable features to this taxonomy. First, we would like it to be rigorous. We would like it to be quantitative so that everybody can agree on it and there's no ambiguity. Unlike the current definition, which specifies that something needs to be nearly round, well, how round is round? This is open to debate, it's open to ambiguity, so we would like the criterion to be quantitative. The second characteristic, we would like it to be easy to implement. So shortly after discovery, we need to be able to classify an object. We don't want to wait thousands of years until we invent interstellar space travel so that we can go there, take a high-resolution image, and decide whether it's a planet or not. We have thousands of bodies that need classification now. The third characteristic is we would like it to be independent of our ideas about formation of planets. And that's simply because our ideas may be incorrect, may be wrong, may need refining. So we would like to keep the classification separate from interpretation at the moment. And finally, if possible, we'd like the classification to follow the spirit of the existing IAU resolution. And the primary distinguishing feature between planets and non-planets in the current resolution is the ability to clear an orbit. It turns out it's possible to write a general criterion for the mass that it takes to clear an extent, specific extent around a planet over a specific time scale. And I won't go through the derivation today, but I'll show you the result because it's relatively simple. This is the criterion, and it depends only on three quantities: the mass of the planet, the mass of the star, and the orbital period of the planet. Now, all three of these quantities can be measured or derived fairly quickly after this discovery of an object. So this criterion is very easy to implement. We can make it even simpler if we want to communicate to the public and hide all the mathematics. We can define a criterion, let's call it pi, which is simply the mass of the planet divided by the corresponding orbit clearing mass. And then if that ratio is larger than 1, we have a planet. If that ratio is less than 1, we don't have a planet. When we apply the criterion to the solar system, this is what we obtain. This is the mass of the bodies in the solar system as a function of semi-major axis. The solid line is the pi equals 1 line. Anything above the line is a planet according to this criterion. Anything below the line is not a planet. And make no mistake about it, we have two types of animals in the solar system. The criterion very clearly distinguishes between 8 bodies above the line and everybody else in the solar system. There are 3 orders of magnitude difference. And this tells us something fundamental about the formation of the planets. So the mere act of classifying these bodies tells us something about nature and about the formation of the planets. When we apply the criterion to over 4,000 Kepler exoplanets, we find that all of them satisfy the criterion. And when we apply the criterion to another 800 non-Kepler exoplanets, we find that all of them satisfy the criterion as well. We're able to classify 99% of known exoplanets with this criterion. The remaining 1% is simply because we don't have estimates of their mass or of their orbital period, which we can easily get. In the process of coming up with this criterion, I came up with another interesting finding, and that is that any body that can clear an orbital zone around its orbit is round. So anybody that satisfies this pi larger than 1 criterion is round. This is important because roundness occurs at a wide range of physical scales. I'm showing examples of a small object that is round and a large object that isn't. Right? The size range at which this happens depends on temperature, depends on the interior properties of the body, interior strength, depends on thermal evolution. None of these things are observable from Earth. Right? So roundness is an inherently hard to implement criterion. It's the weakest part of the definition right now. And the fact that all bodies that can clear their orbits are round allows us to dispense with this superfluous criterion, which is hard to implement in the first place. So the proposed definition is as follows. A planet is a celestial body that is in orbit around one or more stars or stellar remnants. B, has sufficient mass to clear its orbit, and that means pi larger than 1. And C, has a mass below 13 Jupiter masses. We want it to be quantitative, so we can have a footnote to describe what pi larger than 1 means. It's not a very long footnote. It's a relatively simple criterion to implement. So I'll conclude to say, here's a proposal to define planets that applies to all solar system bodies and all known exoplanets. We can immediately classify 99% and can classify the remaining 1% as soon as we have the data, and hopefully this can be used to extend and simplify the IAU planet definition.
Okay, we're open for questions. Please raise your hand and the mic will come to you, and make sure you tell your name and organization. Okay, the first row.
Hi, Nola Red, freelancer. I know that you included the third part, which would exclude brown dwarfs, but I'm just curious to know how brown dwarfs would fit in with the other two parts of your definition as a planet.
Right. Is this on? So this third part of the criterion is based on a recommendation by a working group, an IAU working group, that looked into this issue about brown dwarfs. And so I'm simply restating what the working group recommended, that objects above 13 Jupiter masses not be considered planets.
Sorry, back.
She just asked my question, except that can you just flip back to that slide so I can see the wording of that?
Jay Patsikoff, textbook author. I'm interested in the various things I've just learned. I have two questions. One for Jean-Luc is that why have you excluded lone planets that have escaped from systems? Do they stop being planets if, for example, there's a supernova explosion and they're ejected? And for Robin, I've long used your wonderful models in my textbook. What has led to this advance and this realization? Do you have new computer code, new things going into your models, new ideas that have led you to revise your previous models?
All right, so I'll address the free-floating planets. They're similar to the working group. These free-floating objects are not considered planets. So the IAU still, needs to come up with an appropriate name: free floaters, free floating objects. But
the IAU definitely needs to do something.
right.
So the prior models have been dynamical ones. So what we've done here for the first time is to couple those with thermal and chemical models. So that's the new step. The chemical model had to be we could not simply apply a model developed for the solar nebula. That is a hydrogen-dominated disk at very low pressure. This is an oxygen-dominated disk at very high pressure, so the chemistry was entirely different. So we had to develop a model that could predict the condensation temperatures relevant in this environment, for example. So the dynamical, thermal, and chemical models have been developed separately, the chemical one really for this work, and this is the first time we've combined them.
Questions?
Rick Levitt, freelance. So this one is for Jean-Luc. This is a real question as opposed to the slide. Can you define what it means? Because it seems to clear the orbit. That seems to be a vague definition also. And what happens if you've got resonances?
Right. So the goal of the work was to actually quantify what it means to clear an orbit. And so I didn't show the entire derivation, but the derivation relies on specifying an extent, which in this case is the extent of the planet's feeding zone, and that can be quantified as a number of Hill radii, which is a known physical quantity that we can define very precisely. Depends on the mass of the planet, the mass of the star. And so you can set that extent very specifically. It turns out the criterion is not very sensitive to what you decide, what you choose for that extent. It works regardless. But you can pick the size of the feeding zone, or you can pick roughly half the spacing between tightly packed exoplanets. I show both examples in the paper, and it works either way. Remind me your second.
Resonances.
Oh, resonances, right. So just like the IAU, this criterion does not rule out at all the possibility of objects in resonance. So it's entirely compatible with the existence of a planet. As we know, Jupiter has Trojan asteroids. And in addition, I should point out that a planet can never completely clear its orbit because there's constant influx of asteroids and comets and so on and so forth. So the intent here is really to identify the object that dynamically dominates its neighborhood. And that means that it can either eject all the material in its orbital zone, it can accrete it, or it can control it. All right? So dynamically dominate is probably a better wording than clearing the orbit, but in deference to the IAU, I used the clearing the orbit formulation.
Let me just give a point of historical clarification that most people don't know, because the IAU is not a monolithic organization, and I was present in the vote in 2006, and I voted against it, though I've come around. But this was really a bureaucratic decision. Mike Brown found an object that was mistakenly thought to be bigger than Jupiter, bigger than Pluto. Thank you. Bigger than Pluto. So they had to decide which commission of the IAU got to name it. Was it the Planetary or the Small Body Commission? So anyway, there was a lot of discussion over the 2 weeks in Prague, and finally they came up with somebody in the front writing on the board with a proposal that did not include the clear the orbit business, but it also didn't exclude moons. So I was actually the one who said, raised my hand from the audience and said, what about moons? They could be dwarf planets here, or planets. And they said, oops, and they opened the PowerPoint and made a correction of the PowerPoint. You know, when they're editing the PowerPoint up in the front there, that they're not ready for prime time. And then somebody stood up on the far side and said, I'm the chairman of the dynamical division, and you didn't do anything for our concerns. And he proposed something which wound up being this clear the orbit, which we all know is very imprecise. So it was a bureaucratic point that this last point was added to satisfy one of the commissions of the IAU, and the whole thing was never thought through as a combined proposal the way you are now thinking it through as a unified object.
All right. So if I can address that, I was at the 2006 meeting as well. My recollection is slightly different, but you make a good point that satellites have still not been appropriately defined, and I think the IAU ought to take that up as well, defining what a moon is. I do think it goes beyond a simple bureaucratic requirement. We need to be able to communicate about our discoveries with each other and with the public, and so a proper classification really is needed. The IAU 2006 event was somewhat traumatic because there was an initial proposal that was not released to scientists before it was released to the press, as you may remember. And this was not in the spirit of open inquiry and discussion that we are used to in science. And during the course of that 2-week meeting, indeed, a lot of scientists examined the proposal and realized that really it didn't make a lot of sense. And so they tried to come up in a short period of time with an alternate proposal. And there was a vote, as you say, at the closing business meeting. It probably isn't the perfect language, but I think that given the circumstance, it was probably the best that could be done in that period of time. I agree that it's imperfect, and that's part of the motivation here, is to try to encourage the IAU to revisit this issue and come up with a better classification.
Okay, Rick, we have a few questions on it.
Yes, we have quite a few questions piling up here online. So this first one is for Terry Hurford from Dan Fisher, who's a freelancer in Germany. He's asking, what time scale are we looking at for the groove formation? Is this something that might show up in Phobos images from Mariner 9 compared to Phobos images more recently?
Okay, so Phobos has probably been migrating inward. It could be migrating inward for the age of the solar system. The stresses that I showed in my plot are probably the last 500 million years, and so it's not likely that that we've seen any grooves that have formed since early spacecraft have looked at the surface of Phobos. But that being said, that some of these grooves can be quite young geologically compared to the surface of the satellite.
Okay, and here's a couple of related questions from Irene Klotz of Reuters. She asks, how much time does Phobos have left? That's her first question.
Right, so currently it's decaying at about a meter or two every 100 years. And so we don't think it will decay all the way to the surface of Mars. At some point it will be tidally disrupted, and we think that might occur in about 50 million years or so.
Okay, and then she asks if Phobos' structural instability should be a factor in ongoing plans for human missions, which might include stops at the Martian moons.
I don't think that instability should be a factor. I think it's an exciting location to go to because of this. I think you can learn a lot about the structure of Phobos. One of the exciting things about the model that we put together is that we predict that the interior needs to be weaker than this exterior layer of regolith. And so that's something that you can test, and that's something that astronauts, when they go to Phobos, could test with equipment that they bring with them. And so it makes it a really exciting place to go as a precursor to going to Mars.
Okay, now we have a question from Leo Enright from Irish Television for Apostolos Christou. He's asking if there's a way to test your hypothesis at Mars or at Earth, where there are satellites in orbit, whether they can identify a comet that's orbit intersects with the planet, and whether you can predict that you'll see an increase in meteoroids at a particular time.
Right. So one way to try to test this Encke stream hypothesis is because we know that the dust would impact on the night side of Mercury. We can actually have a camera to look for impact flashes. That's probably one way. The other way, I suppose, is to have a dust detector on an orbiting spacecraft to pick up the ejecta that's actually lifted off the surface of Mercury as it goes through the stream.
Well, I think Mr. Enright's question was more about whether a similar kind of test could be done around Earth or Mars, where we have a lot of spacecraft in orbit already, as opposed to at Mercury.
Oh, you mean...
Like, can you predict when you should see a similar enhancement around Earth or Mars, and then make observations with orbiting spacecraft to confirm the prediction that you're seeing this enhancement?
Sorry, I misunderstood. Okay, so Mercury and Mars, Earth and Mars, they have quite thick atmosphere. So if Encke dust hits two planets, we won't see an exosphere, but rather we'll see meteors in the atmosphere. And we actually do see meteors in the atmosphere of the Earth, which are caused by dust by Encke, which is a torrid meteor shower, which actually peaks right about now. So we know that the stream exists, and actually it extends quite far away from the orbit of Encke, because the comet is not actually the comet's orbit is not actually that far away, but close to the orbit of the Earth. For Mars, I suppose the thing to do would be to put either a camera in orbit around Mars to look down on the atmosphere to look for meteors, or put a camera on the surface to look up to see the meteors, in the same way that we have cameras looking for meteors at the Earth.
Okay, we're done online.
Okay. Any more questions? Oh, Rich.
This is for Jean-Luc. A quick question. Rich Talcott from Astronomy Magazine. Not having your equation in front of me, I'm just curious whether the pulsar planets should be considered planets now, or are they too small?
Great question. I tested the criterion on pulsar planets, and they're all planets according to the criterion.
Is that where stars or stellar remnants came from?
That's correct.
Hi, Stephen Battersby, freelance as well. So I have a question for Jean-Luc about how the definition handles binary planets or co-orbitals. Are there any ambiguities there?
No, that's a great question also. So we haven't found co-orbital planets yet, but we can't rule them out. And the idea in the criterion is that if each object individually satisfies the criterion, it should be considered a planet. If one of the members doesn't qualify, then it should be considered more like a Trojan asteroid. The same idea for potentially double planets. It's really the mass of the two bodies that does the clearing of the orbit. And so the idea there is the same. If each body individually satisfies the criterion, you could have a double planet, and otherwise you could call that a two-body planet or planet plus satellite system.
Okay, I mean that's interesting. Because that would suggest that you could have a very large planet with a moon where the barycenter was inside the planet, but if that moon is still massive enough, if it were on its own to clear the orbital neighborhood, that would be classed as a planet, not a moon.
This criterion makes no reference to the barycenter, to where the barycenter is. It just looks at the ability of any one object to clear the orbit. Yeah.
Okay. Any more questions? All right, we'll wrap it up for today, and we'll see you at noon tomorrow. Thank you.